Hi everybody, so we're looking at pH and indicators again, and this time we're going to look at 2012 question 10b. We've seen something similar to it before, but I like this one because even though it's similar to one before, it's a tiny bit different. So look, let's start. A certain water soluble acid-base indicator represented by HLN is a weak acid and dissociates in water as follows. And we're given dissociation there. Okay, that's grand. Now, you are asked to state and explain the colour observed when a few drops of solution of the indicator are added to the hydroxide solution. Okay, so this is what we have here. You're asked to state and explain what happens if you add the indicator to a hydroxide solution. Well, we go back to what we've seen in exams before in terms of dissociation and experiments. And usually when we add the two together, it goes a purpley color. It'll go from green to purple. Okay, so if you add in more HLN here, okay, what'll happen there is it'll go towards the right hand side because of chemical equilibrium and the Rydellier's principle. Okay, and you'll get your purple color. Okay, observed, and that ties back to chemical equilibrium. So that's kind of slightly different to acids and bases, but nonetheless, it does tie in with chemical equilibrium a small bit. If you haven't done it just yet, I wouldn't worry about it too much. Let's look at the actual question though for pH indicators. You're asked to calculate the pH of sodium hydroxide solution there. Okay, so sodium hydroxide, you have to turn it off, is a strong acid, and strong acids. So we'll do strong acid here. Strong acids won't have a dissociation constant. Okay, now write down your overall formula here. Okay, which is for a base, it's pH equals 14 minus the POH. Okay, now for a strong acid, the POH, I know my writing is awful, but it'll have to do minus log the base 10 and your square bracket there, and that's going to be your OH minus there. Okay, so we'll calculate the POH and then we'll plug it into the formula up here. So let's see what we have. POH equals minus log, and we are dealing with 0.5. So just plug that straight into your calculator there. Okay, and when you plug POH minus log into your calculator there, you're going to get 0.3. So we come back over here, pH equals 14 minus 0.3, pH equals 13.7. Okay, and that makes sense because sodium hydroxide is a strong base, okay, and therefore should be close to the 14 mark. So we have the first one done there, okay, in which we were asked to find out the pH of the sodium hydroxide solution. Now next to it, you're asked to find out the pH again, calculate the pH of a 0.1 molar solution of the indicator, and you're given a Ka value. Now, first things first, we know that the indicator we're dealing with is a weak acid, and that's obvious because you're given a dissociation constant for the acid, okay, the Ka. So we just come back down here, and I'm going to write down part 2 here just to keep things separate. And we have a slightly different formula, so the pH equals minus log the base 10 square root your Ka multiplied by your molarity. Okay, so in this case here, the H plus ion concentration. Okay, so all we're going to do now is plug in the data that we have from up above. So minus log to base 10, and Ka is 2 times 10 to the power 5. I always put this into brackets because I'll put them into brackets when in the calculator as well. And our molarity is 0.1. Okay, so as I've stated before in the past videos, do not plug that into a calculator. Do it out separately because you're less likely to make a mistake. Okay, so if we bracket 2 times 10 to the power of minus 5, close the brackets, and we're multiplying that by, was it 0.1? Definitely was. It was. Okay, we multiply that by 0.1, and we're going to get 2 times 10 to the power of minus 6. Now you can plug everything else into the calculator now, okay? Because you'll get that out fine, okay? And if you do that into the calculator, then you're going to get 2.85. 2.85. So we'll just highlight that. And it makes sense because 2.85 is a weak acid really. Anything under 2 or under is considered to be a strong acid. I know it can vary for some people, but usually under 2 is a strong acid. So that's grand. Okay, we have that undone there now. So I just did this one because there was a little bit of chemical equilibrium brought in here. Okay, so if you're adding more of the indicator over here, according to Taylor's principle, okay, the system will shift to relieve the pressure that's been applied as such, and in this case here, it'll go a purple color. Okay, so look, I hope that helped. I'm going to be doing one more video after this, and I'll be talking to you then, I suppose.